Good morning, Matthew. Thank you. That's awesome. You win. Not that it's a competition, but good morning, Matthew. Thank you for saying so. Oh, and okay. Everybody, okay, we'll give a couple of minutes. Give me a couple of minutes. Good morning, Eric. Thank you. The man knows. These men know. They know the Zoom Yaverbaum approach. Good morning, Francis. Good to see you. Oh, good to read you. Right. So, good morning, Jonathan. Awesome. All right. Right. Because yes, thank you, Jonathan. Okay. You see the point. Okay. And good morning, Melita. Awesome. Awesome. And yes, will I take the entire class to do this? No, but will it feel like it? Yes. For good or for bad, I'm a hello person. Okay. So yes. And here's comes everybody. Um, okay, okay. As you can see, this truly is synchronous. Just when you thought the only thing worse than having your life invaded by Yaverbaum at 8 o'clock in the morning for 2.5 hours of physics is having your life invaded by Yaverbaum at 8 o'clock in the morning in your house. I know, in the house. I know it's horrible. It is kind of hard. I know, I know. But hello, hello. But who else? How is that? So good morning. So I see. Hello, Tania. Hello, Billy. Who else have I not? Wait, I'm looking in the chat. And we'll talk about video and all that. Yes. So, okay. Right. So absolutely. Good morning, Matthew. Good morning, Eric. Good morning, Francis. Good morning, Jonathan. Good morning, Melita. Thank you all for, and then I'm also saying, good morning, Claudia. Good morning, Tania. Wait, whose name I'm, now that we're not live, when I look in your face, Tania, I know how to say your name. Wait.
Oh yeah, it's Tanaya.
Darn it. I see, I knew I was doing it wrong. Sorry, but thank you. And that counts as a good morning. Thank you for acknowledging with your voice. Also, you get points for that. We'll talk about that in a second. But Tanaya, I'm sorry. I really will get that right eventually. And I really think that when I look at you, I get it right. Anyway,
Yes.
I like physics. I like physics. Tanaya likes physics. Okay. And there's Claudia. Good morning, Claudia. Okay. Good to see you. All right. And there's, oh, and Sharon. Good morning, Sharon. I think that's everybody. I think, um, okay. Okay. Oh, no, here comes more people. Here comes Yassine. Also mispronounced Yassine. Yassine. Okay. We will do physics in a moment, I promise. It's a slow warm here. I hope you guys at least have coffee, or whatever. Or chai latte. Does Starbucks deliver? No, not yet. Someday the app will just deliver. Okay. Okay. Oh, no, here comes more people. Okay. We will start. So, okay. Obviously, we're warming here, warming up. Um, so, and of course, okay, so it's weird that we're on Zoom. I know. I totally appreciate that everybody is making this effort at 8 in the morning to be on Zoom. I know it's in some ways easier than dragging all the way to school, but in some ways I know it's harder. In a way, and it's harder to log on. It's harder to get, and it's harder to stay tuned. I know all this, uh, and I feel your pain. But I appreciate that everybody's here, and well, that all of you who are here are here. And I appreciate that you sent back the confirmation last night. I think there is one person who sent it this morning, and I will. Obviously, if you sent it by midnight, you got all 5 points. If you sent it this morning, I did get it. I haven't returned it yet, and you'll get 3 out of the 5 points, which I think is still, just because whatever. But I appreciate that you all confirmed. It's just like a way of making sure we're all on the same page. Partly, and okay, here we are going to do physics. I promise. Here we go. I'll start getting myself the board. Should Yes, that is the board. Right. Okay. So this is the whiteboard. So obviously, some of the people in the room have had me on Zoom a lot and know how it works. Some of you have not had me on Zoom. Why we're doing this today. Well, the college told us to, of course, but and why we're not canceling entirely. Believe me, it occurred. I thought about it, but we can't cancel entirely because we only meet once a week. So we would fall substantially behind if we canceled entirely. I will try to make this as livable as possible for everybody. I will say that and if we blast through where we need to get through, I'm not above letting you go early. In fact, I'd even rather, if it's possible, I'll try to like blast through what would be a break and just end a little bit early. I will try to do that. I know it's a lot to sit through Zoom for 2.5 hours is a lot. I'm very aware. Um, and there's only so much you can absorb anyway. I get that. So partly we're here together for continuity because we go 2 weeks without even seeing each other, and then physics completely drifts from our brains. Um, Also, we're here together to be clear too. The other reason we're here together on Zoom today is is to kind of break the Zoom seal, so to speak. That is to say, there are some resources and aspects of this class that like originally were designed during COVID or are more obvious and easier to take advantage of for the online versions of this class. Now, again, I think in the end, you're doing really the right decision by choosing to take the non-online version. I think in the end, it's better for you. But there are a couple of perks and a couple of things that we do in this class electronically that the fact that we were sort of forced to go on Zoom today can make more easy for you to use and be aware of. They can just sort of break the seal on that. And I'm going to explain that what I mean in like 1 second. And I'll also just say, since it is possible between now and the end of the semester that something will happen to me or something where I have to, at the last minute, change the class and make it online. If that happens, like if I'm sick or something, and some of you know, I travel a fairly large distance to get to this class. So if travel breaks down or something at some point, if we ever have to go online again, at least now the good news is like we know the system. Like the system is that you'll get that notification from me from Google that you got last night. That by this point, I actually believe every single one of you actually responded to. Like one of you responded this morning. Okay, that's not ideal, but like whatever, I saw it. So that's the system. If I ever have to cancel, go online, I'll send you the notification. You'll get points just for confirming and responding. And even when you do that and you get the points for responding, that doesn't that still, if then you get into something happens and you don't make it to class, it doesn't matter. You still got the points for confirming your understanding. Okay. So that, and it'll be this same Zoom address and all of that. So at least now we know in case this has to happen again, like this is how it works. But I also want you to know, especially those of you who never had me on Zoom before, like you might notice this is being recorded. Okay. It is being recorded, the recording of this. And I hope that doesn't decrease your participation or whatever. I mean, I understand why it does, but like nobody really cares about these recordings besides the John Jay students for whom they're meant. So it is being recorded and it will be posted to the YouTube channel like this afternoon. Okay. And the good news of that, and you'll get a notification in Google Classroom. Once this class, the recording of this class is posted to YouTube, you'll get the notification. So obviously, to whatever extent it's hard to stay tuned today, or if you have to go in and out or whatever, like it'll all be there and you can use it later and watch it when we have an exam or something. And it's good to know about that. And again, obviously people who have this as a Zoom class, like sort of use that all the time. It's less obvious to you people, but the fact is when I post this to the playlist that's called P204 SP24, like Physics 204 Spring 24. When I post it to that playlist, what you'll see there that you might not have known before or cared before is you'll see all of the classes from the online version of this class from this semester, like all of which are, the same material and the same curriculum and basically the same schedule as yours. So it's a good, and you'll also see that there are playlists of Physics 204 going back every semester since the beginning of COVID. Okay, obviously I always say, it's always the same curriculum, but I'm like a slightly different approach, different emphasis every single time. So it is a good resource just to know that when we come toward the exam, or if you miss a class or blah, 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 you are welcome to go. And I try to make the titles of the classes better and better these days, like more obvious, like to what they are. And some of the classes I even put chapters in and stuff so that you can skip around and skip all the dead air and the hellos and all that. Like it takes a lot of, some of them are. So just please know that you are welcome to use the YouTube channel and find any old version of any class, or if like you caught a class and I just didn't say it right for you, you need like a slightly different version. Like there's a million different versions of the same material up there. So this is just like a good way so that you can know that, okay? And yes, one of the game portals is if you even just show any indication that you've ever used that resource at all. If you've ever watched a video, even or scroll, and of course you don't watch them. I mean, I know, you scroll around and you like put an earphone in your ear while you're doing dishes or whatever. And I mean, of course, you don't like watch. I mean, I can't even, but you know what I'm saying. You just use them as a resource. And if you ever do, there is a game portal where if you just show a screenshot that you even once used a YouTube or subscribed or whatever, you get points for that. Okay. Then furthermore, and I'm almost done with all this, but just so you know, again, since we've never done Zoom before, I'm just like trying to acquaint you all to like how I approach Zoom. I know, and obviously there's some people, for example, you see some people, some old reliable friends of mine, Melita and Claudia, are showing video, right? So what's up with that? Like, thank you. I thank them for that. Does that mean you have to? No, obviously I'm not yelling at anybody for not doing it. But, oh, and sorry, there's something in the chat. Sorry. I am a big chat person. Oh. No, and you're totally right. Oh my God. Perfect example of something. Okay, so someone just posted. So I'm going to break for a second because someone just posted something in the direct. No, that's perfect. Yes. Someone actually 3 minutes ago, I missed it. I'm so ashamed. Someone posted something in the direct chat. So I want to talk about that for a minute. And it said, I'm not going to say their name. That's my point. But they are saying in the direct chat, wait, is game turn 3 posted yet? And he or she is correct. I failed. I will by the end in a few minutes. I will. I have not posted tonight's game turn yet. I was about to do it right before this class, and I didn't. So good point. Thank you. I will post it shortly. Thank you for the reminder, and thank you for caring. And I'm not being sarcastic. But then on that, also, when I post the game, maybe I'll do it in like 1 second. When I post the game turn 3, is it only is this our third class? It's not our is that our fourth? It's our third class? Yeah, I guess that's right. Wow. See, it's a good thing we're not canceled. All right. You'll also note now that we're on Zoom today, you'll note that there are some game portals that really, really apply much more to Zoom than to in-class, but they're totally yours to take advantage of. Like, for example, and again, I'm saying this mostly, for the benefit of people that I don't know as well yet. Like, if you are not obligated to show video, there's 1,000 reasons I understand why it's rough to show video. However, if you show it for even 2 minutes, it really is a huge benefit to me and to the class. If you show video even at all, like, not to call them out, but like, for example, thank you, Melita and Claudia. If you show video at all, there's a portal where you just like screenshot the fact you showed video, put it in and submit it, a game portal. I mean, I think it's called video, and and you get points for that. Okay. And part of the reason, and there's other things like that too, like if you use the chat at all, or as for example, I believe Tanaya already did this. Tanaya used her voice today while we're on Zoom. Okay. That takes guts. It takes a bunch of things. It's super, and it super helps the class for anybody ever to hear anybody besides me. So there's a portal for that. I mean, the truth is, it can also be applied to regular class, but you might not have noticed it or cared. There's a portal that says something like speak or forever hold your, it says something like speak or voice or something, some cutesy title. So she should submit to that and get points for the fact that she used her voice at all. And with all of these things, especially video, I'm very, and I know I'm talking a lot about this, but again, I'm sort of laying the groundwork in case we ever have to go on Zoom again, which is quite possible. Like, I want you to know that I know that one of the reasons people don't show video, one of the reasons people, including faculty members during faculty meetings, don't show video is because half consciously they're afraid that even if they could show video at that moment, they think that the minute they turn it off to go to the bathroom or whatever, the minute they turn it off, the turning it off is going to be even more blatantly noticed and like problematic than if they just never turned it on at all. I understand everybody thinks that, and I'm not saying that's not crazy, but I'm here to tell you, like, please know, any minute that you ever do anything to break up the monotony of me in talking is a good thing. If you like, if Melita turned off her video right now, I would not be insulted and I would not be suspicious. And I would just be like, I'm glad she had it on for 5 minutes. honestly. So all of these kind of things, or so if you go in the chat, don't think that means that you have to go in the chat like forever. It just means you see what happens. If I get in my own head on Zoom like this and I don't get broken up by you guys, I'm just gonna go and leave everybody in the dust. Like, so there's a lot of portals to reward a lot of that kind of participation. It's all good, and the lack of it is not punished. The presence of it is rewarded. Okay. Now, oh, there you go. Thank you, Melinda. There you go. All right. That's awesome. So, and we're almost, okay. So yes, and she gets, and there's various ways she can get points for even doing that. Awesome. Okay. I'll even say, like, there's another, okay, I'm over talking this. She can triple dip that little contribution. It's like 3 different places that I can think of. So if you ever look at a title and it's so cutesy that you don't even understand what it means, like text me or chat me, right? I'll explain it. But like okay, because there's like one multiplayer co-op. I think I'm willing to say that what she just did counts because she just helped me out. There's one like closing a conversational path. I believe that you could stretch, and she can't. All right, so that's great. Plus that's an image, right? Okay, I'll stop. But like, notice that what Melina just put in, it wasn't even just like her typing. It was like literally she pasted an image that counts as an image. So there's one that's like something like something is worth 1,000 words, like some cutesy. If you post any kind of image or graphic or into the chat, it helps us all stay alive. So you get points for that. Finally, I know I'm getting to, I haven't even had my coffee yet, believe it or not. Oh my God, but I'm looking at it. Finally, the person, in terms of direct chat, this is important, actually. I honestly believe at this point in my career that the one biggest thing that Zoom gives us that a regular class does not give us, and again, I'm saying this, still preferring regular classes, okay? But the one thing you can do on Zoom that you cannot at all do in a regular class is direct chat, right? Like, I actually find this profound. Forgive me for dwelling on it for a minute. In a regular class, at best, maybe while everybody's doing group work, you could call over the professor and ask the professor something in private, or even ask the professor to step outside the room and ask the professor something in private. Like, you could do that. But then, of course, everybody knows you're doing that, right? Even if they don't know the content of what you're saying, they still know that you're calling yourself, right? And that, like, who wants to do that? That's very uncomfortable. But here, I just want to remind you that you can send a chat that literally no one even knows that you've sent it to me. And I think that is like really, I have come to believe that that is super helpful for everybody. So my pledge to you is I do try to pay attention to the chat. I sometimes fall behind a couple of minutes, but I really do keep the window up. And I really will stop on a dime for the chat because I'd rather it be you than me running the show. And anything that comes in the direct chat, I will totally honor. And what I will do, just to be clear, like I did 5 minutes ago, if something comes in the direct chat, I will not say the person's name. But if I think that, and if it's like super private, if it's like, can we make an appointment? I don't know, then I will like literally just respond in the direct chat. But if it's something that could help the whole class, like someone just did 5 minutes ago, I will repeat the content for the whole class, but I won't repeat the name. Okay. Long way of saying, I think the chat is like a hugely important function to keep us all alive in the class, and the direct chat even more so. Sometimes, including today, I might give little exercises where I wait for each and every one of you to give an answer or a question in the direct chat before I move on. And I have found that that can be a very valuable thing that we can. So anyway, please use the chat. I will follow it. I'm looking right now as a matter of fact. Okay, I'm looking right now. There's nothing more in the chat. So we are going to do physics, I promise. Oh, and thank you. Oh my God. So all these people are showing video now. See, oh, thank you, Jonathan. Thank you, Tanaya. Thank you, Eric. I totally get it. That's awesome. And you have not, and even Yun, who, wow. Okay, awesome, awesome. Yes. So that counts. And if you end up turning it off now, I will, it also, by the way, all of you who just showed video, like after I said show video, I think that also counts in the same way that Melina's count. Like, I think that also counts as closing a conversational path, because like you're showing that you heard that I just said something. So you could like double dip that, I promise. Now I'm going to pause. What I'm first going to do is honor the direct chat by like making sure right now to post that thing that I didn't post yet before I forget. Hang on. And then I don't think there's more homework to post besides, I don't think. I think I also still owe you feedback. Oh, wait, I could have sworn. Oh, and some of you didn't get back. Wait, I'm looking right now. I apologize. I could have sworn that I sent back all of, Wait, why didn't it return? All right, some of you did not get back the 5 points. I'm looking right now. I swear, in the middle of the night, I thought that I returned all of these. Maybe I didn't hit return. But I know that all of you did return the 5 point thing last night. I mean, I see it here as drafts. Why didn't it return? Okay, I don't know why it didn't return. That's what I get for doing the middle of the night. So they're coming right now. And again, in general, just so everybody knows, if anything has a midnight deadline, if anything, I know this is confusing. Some people ask about this for the new people. I'm bizarrely strange about deadlines. On the real homework that really counts, like that's really physics and problem solving, I'm surprisingly loose about deadlines there. Like you get rewards for being early, but like but I want you to keep revising and re-uploading, and I know I fall behind. So there's always a lot of, so eventually on all the physics homework, eventually everybody can get all the points, even if it takes a while or it comes in late. Okay, with the actual hard stuff, there's more flexibility on time. But with the little stuff, with these game turns, anything that's due at a midnight, the truth is if it comes in the next day, I give 3 points instead of 5 or whatever. Partly because I think that stuff is not hard to do. Like if you just remember to do it, you just do it. It takes 2 seconds and it's relevant to the day. It loses its relevance after a day, but also to keep you in the habit of just knowing that as loose as I am about deadlines on physics homework, I'm not loose about deadlines on the exams. So I don't want that to come to a shock to people when we get to exams. Like we do have to be strict about that. So partly for that reason. So I'm just explaining that right now, if you turned in the 5 point thing like this that said it was due at midnight last night, if you turned it in this morning, you're getting 3 points instead of 5. Same thing with any game turn. If you turn in the next day, you get 3 points instead of 5. I don't think it's a big deal, but it's just to enforce the habit. Okay, so hopefully you all just got that back right now. Hopefully to let me know if you didn't. Now I'm just doing the thing that the direct chat person said, and then we will start. Yes, he or she is definitely right that I did not, that it is the third class and I didn't do it. Okay, hold on. Sorry, coming right now. I will shut up. Again, I know this is a lot, or it's not enough. Where did it go? Okay. Oh, and while I'm doing this too, the other thing I should have made clear about Zoom classes with me is that, okay, here comes game turn 3. Maybe let me know in the chat if you let me know in the chat if you confirm that you see it and it's correct. That also counts as participation. And as far as game turn 3, I'm sure this is clear to you too. You know, even just saying hello, like in the chat, counts as participation for today. And that's why you notice that all the people that have had me before, like all did that. Like just saying hello in the chat counts as participation for today. Okay. Okay. Oh, or good morning.
We
Yes.
see it.
Oh, wait. Good morning, Billy. And wait, who just said it? Wait, someone just said that. Wait.
We see it. It's up.
Oh, thank you, Melita. Okay, so she sees this up. So that just counts as her also using her voice. So literally, like, some of you have already gotten like literally like 14 points just for existing today. Like, not to be, but again, anything we can do to keep us alive on Zoom for 2.5 hours is good. All right, so good morning, Billy. Thank you. Okay. So now, we're gonna go to physics. We're gonna go back to homework 1B. These equations that you see on the board are like where we're going today. They're like the goal of today. They're not. Oh, awesome. Thank you, Tanaya. Thank you, Tanaya. I'm going to start giving you, all right, like serious? Oh, I will. Remind me. Anybody can text me right. I will open up a portal from here on in. Anytime I mispronounce someone's name and they gently point it out in the portal, if they politely are like, yeah, you mispronounced my name today, I will literally give points. I don't know why I didn't think of this years ago. That's for everybody. It's not just for Tanaya. But if I mispronounce your name and you politely point it out, remind me, I will make a portal for that because I need to stop doing that. Okay, but so thank you. And Tanaya gets points for going in the chat and for closing the loop. So great, as does Melita. So the equations that are on the board right now are the like goal of where I'm going to get to. They're not a review. That's not like expected that you already understand them. That's where I'm heading today. Specifically, I'm heading there with the rest of homework 1B that we now have to start going over. Last thing to say that I almost forgot is this board that you see, that I hope you see, this whiteboard. This, as you might know, when we're done with the class, it's a PDF. It will get uploaded to your Google Classroom. So you'll get these notes, you'll get the video. It's all understood. Any notes that you can, I encourage you to take notes anyway for 1,000 reasons. I don't think I have to tell you that. And I encourage you to write down things that I say, but don't write down. And that's a portal too. If you ever screenshot anything you wrote down that I didn't like literally hand you on a written silver platter, you get, that's some portal that's called like notes or well noted or something. You can get points for that. All right, but now that this is all clear, you could stop me anytime. You see it. Okay. Oh, what is it? Oh, okay. Oh, and good morning, Yiyun. Thank you. Awesome. Awesome. Okay. Claudia is getting us off the ground here, getting me back on track with a great opening question. All right, I will start with Claudia's question. Sorry, and I did bring a cough drop. I did. It started. I did bring a cough drop. Okay. Let me start with Claudia's question. Okay, I will say, to be clear, this is all ultimately relevant to homework 1B. And I know that where we left off last time was question 5. So let me just put us in context here. We are in homework 1B, but yes, Claudia's question is a great one. I'll get to that in 1 second. Homework 1B continued. And I'll even say this here, yes. Questions 4 and 5 revisited, expanded. Okay. So what I'm doing, just to be clear, and again, this is what I was going to do, but also to answer Claudia's question. Question 4 and 5, we answered in class. Like we went through them, we got answers. But we did certain steps that I don't feel yet have been fully explained. Specifically, we used a thing called mechanical energy conservation, which involved kinetic and potential energy and work. In theory, you learned about work and kinetic energy last semester, but perhaps quite quickly. I don't believe everybody has fully seen an expansion of what potential energy means or where it comes from. That's what I want to back up and explain now. And that's where the circle on the integral comes into play that Claudia's asking about. Okay. Okay. So the short answer. So Claudia asked in the chat, what does the circle on that integral mean? Very fair question. Because you've never seen one so far in physics, and you may never have seen one so far in math. The fast, simple answer, well, is that circle turns an integral into what's called a closed integral. Specifically, so I'm going to expand on this right now, but just to give you an answer, specifically the integral, well, Okay, let me start with this. So again, this is in effort to answer Claudia's very good question, but it's like I'm going to do it by contrast. Like, first of all, one thing that is supposedly known from Physics 203 is work is defined as an integral, specifically an integral of force. More specifically, work is the integral of the dot product of force vector with displacement vector, right? Like if you look at it, like that's what it is. It's the integral of f dot dx. And dx and f both have arrows above them. They're both vectors. One is a force vector. The other, the infinitesimal, the dx, the infinitesimal independent variable is a displacement. Whenever you see that construct, ever in physics or math, if you see an integral of some dependent variable dotted with a displacement variable, then what you're seeing is you're seeing an integral of some measurement being taken along a path. Like what I'm trying to emphasize here is the fact that the independent variable, the dx, the fact that the independent variable is literally a space variable. Like it's not time, and it's not force, and it's not velocity, and it's not something else like that, or acceleration or whatever. It's literally dx, like an infinite dx means an infinitesimal step along an x-axis, along a path of space. So what this integral is asking is like for you to take small steps along a path, and each step you take, ask what's the value of the force? How strong is the force along this step, right? It's literally, and again, I know I've said this a million, but integrals take a lot of getting used to. What this integral is asking you to do is take an infinitesimal step forward, and then look up and ask how hard, how strong, how many newtons is acting right now on whatever. And it's asking you to take that number of newtons, multiply it by the infinitesimal number of meters that you just stepped, right? Multiply them together, put them in your bag, in your mind, and then take the next step and do the same operation again. Ask, how big a step did I just take? Multiply by how big was the force right there? Multiply them together, throw them into your bag, and take another step. And add up all of these products, like after you're done walking the entire path, add up all of these products, and the full the full sum of all of the force times displacement products. That's what the integral is, right? Now, again, like for some of you, that's old news. For some of you, you're still getting used to that. But integral does always mean continuous sum of products. And it's always the case that the independent variable, the dx, right, is infinitesimal. So every step you take is teeny tiny, infinitely small, and each one is the same size. Each one is literally the same infinitely small size. And each one, you stop and ask the question, how big is the force right now? The force presumably keeps on varying. That's why you're doing this. And then you just add up all those products, whenever the steps you're taking are literally steps in space, right? Like you're always taking steps on the x-axis of something, but the x-axis could represent anything mathematically. But if specifically the x-axis really represents walking in space, as it does here, then the type of integral we're talking about is called a path integral, and it is taken from one point in the path to the final point in the path. So now that's what work is. It is a path integral of force, and path integrals are definite integrals. Like it's from a certain space point in the path to a definite place at the end of the path. Okay, right? So you get you don't get a plus C, if you know what I'm saying. You actually evaluate at the end and you get an actual answer. That's what a path integral is. Now, I've got to contrast this with what Claudia is asking about and what the whole point of this class is. But I have to say one more thing before I do that, just to remind you of the context of all of this, or like, why do we care? Like, why do we care about this path integral? Okay, now again, just to get, like, this is all what I am intending to teach today. This is not off the topic. This is the topic, but it still hasn't answered Claudia's question yet. I know that. I'm just like, I'm going through I'm just like going one step at a time. And I'll definitely let you know when I get to the answer to Claudia's question. But here's a reminder. This is technically a reminder from last semester, but it's subtle and important for the rest of this semester. Notice what I'm doing now on this page is I'm giving you a different equation for work, right? It almost looks like I'm giving you, I mean, it does. I am giving you two different equations for work. That could seem confusing. Like, which one do you use when? Or like, is it a contradiction or what? Please note that on this page, on the first page, I gave you a triple equal sign. There, I'm telling you what work is. I'm defining what work is the path integral of force, right? Which means the continuous sum of force displacement products. That's what work is. Now, on this page, what I'm reminding you is that what work does. So it's now a double equal sign. The consequence of work, what it does is it transfers 1f squared. And we did the algebra to show, why do I know this? Because of like 3 lines of algebra that we did last semester that I could happily redo for anybody at any time. If you privately text me or whatever, I could show you. But it's basically just using the definition of using F net equals MA and plugging that into the definition of work. What you see is that when, well, technically speaking, when the net work done on something, like if you add up all of the forces doing work on an object, if you add up all the forces and take into account negative signs and all that, what you find is that by doing work on an object, you change its value of 1f mv squared from some old value to some new value. That's what you just find algebraically. Therefore, we start paying attention to this construct of 1f mv squared. Like, it's just the combination of measurements that seems to change precisely when you do net work on something. Okay, so nobody ever cared about 1f mv squared before until they did the algebra and found out, like, oh, and when I say doing work on something changes the 1f mv squared, I mean precisely what I mean is this. I mean, if you look at an object and you take its mass, and you look at an object at a certain moment, and you take its mass and you take its instantaneous speed, like at that instant, at that moment, right? So you take its instantaneous speed and you square it, and you multiply it by its mass, and you divide the whole thing by 2, right? Like, which you would never do if the algebra didn't like tell you to. Like, no one would ever think to care about that. But it turns out, if you square the speed of an object at a given moment and you multiply by half of its mass, or you multiply by its mass and you divide by 2, right? You get a number. That number you get, if you work through the units, which you can, which we did last semester, I can help you with. If you work through the units, you'll find that the number you get is in the units of joules of kilograms times meter per second squared times meters. Like, that's a joule. That's right. So you just write that number down. Like, okay, I'm looking at this object. It has a certain number of joules of 1f mv squared joules, and you write it down. Then if you come along and do work on the object, if you push it through a displacement or you pull it through a displacement, and at the end of the pull or the push, now it's moving at a different speed, right? Because you're like pulling or pushing it, you've accelerated it. If you now, at the end of that journey, if you take the measurements again and you write down the speed squared now times the 1/2 mass now. You'll get a different number also in joules, right? And you find that the difference in those two joule numbers, is exactly the number of joules of work that you did on the object. Okay, I'm not saying, duh, obviously that would be true. I'm not saying, can't you see why that makes sense? I'm saying it turns out to make sense if you do the algebra, or it turns out to be true if you do the algebra. So it turns out to be the reason that we care about work is that what work does is it changes the amount of 1/2 mv squared that an object has. So from here, and it changes it precisely, like joule for joule. So from here on in, we track 1/2 mv squared an object and we call it kinetic energy. We say, because so literally, if I do positive work on you, you gain that many joules of 1/2 mv squared. And where do they come from? They come from me. I will lose. If I'm a billiard ball and I smash into you, you're a different billiard ball, right? You'll start moving faster. I'll start moving slower. And exactly by this amount that's predicted by right here. So from now on, the way we look at the world, what we look at the world is work is the transaction, energy is the commodity. Right? Work is the verb, energy is the noun. And again, I know I said this for some of you, this is old news. Some of you, it's not. I'm just trying to clarify. And then I'm going to contrast all of this. I'm going to then take this a step further to show you how this leads to potential energy, which ultimately will answer Claudia's question. But what I'm saying right here is, what work does is it transfers energy. What energy is the ability to do work. It sounds like you'll know that you understand or that you're hearing what I'm saying if it sounds sort of circular. If it's sort of clear, but sort of sounds ridiculous, you probably understand me. Because what I'm saying is, what's work? If I say, what does work do? It transfers energy. And then you go, okay, fine. What's energy? And I go, well, energy is the ability to do work. If that sounds like a circle to you, you're sort of right. But it's not really a circle. It ultimately means something. Just like saying, what is a transaction? A transaction is when I spend money or gain money, right? And what is the point of money? The ability to perform transactions, right? Why do I want money? So that I can spend it, right? Now, why does that make sense? Because when I spend money, I get something of equal value in a different form. I want $5 so that I have $5 to spend. What do I spend it on? A pack of Pokemon cards. Now they're equal to $5 according to the market. Like in some deep sense, I didn't, because now I have a pack of Pokemon cards in my wallet, in my pocket. In some sense, nothing changed because now I can go sell that pack for $5. So in some sense, the whole time I just have $5 of value in my pocket. But sometimes I want money and sometimes I want Pokemon cards. Like they perform different functions, right? Like I don't need to over-explain this. Same thing with energy. Energy is just a ball that we pass around. The more energy you have, the more you can pass around. But why do you care? Why do you ever do that? Because it comes in different forms. Sometimes you want, and that's what we're getting into now with Claudia's question with potential. Okay, but simply put, work is pushing or pulling something through space. That is really what work is one object interacting with another to shove it through space. And what is kinetic energy? Or what is energy? Is your ability to do that. Why would you have the ability to do that? Well, the form that comes from that little algebra, kinetic energy specifically, is the ability to do work by virtue of motion. Hello. Okay, just to be clear, and again, I know, sorry, when I'm looking at the chat, so there's a transfer. Yeah, actually, that's really, it's so, I should open up a portal for this. And I'm noticing it's very nice that Claudia was willing to ask a second question, even when her first question still hasn't really gotten answered yet. That shows deep faith. I appreciate it. But yes, so, and I still am going to answer her first question. I promise. It's just that she's just happens to be sort of like 2 steps ahead of me. But her second question here in the chat, where it says, so there's a transfer of the ability to perform work. That's really cool. So the answer is yes. Yes, there is. But I see what she's doing, or I think I know what she's like taking my words and like putting them together and saying, well, like if I really take your word, if you're really defining work to be this and you're defining like energy to be that, then you're really, if I put all your words together, you're really saying something kind of strange, or like you're actually saying, Yaverbaum, that you can like transfer an ability. And you know what? I'm saying good point. Like I hadn't quite thought of it that way exactly, but yes, that is what I'm saying. I am literally saying, so yes, and we're going to move on in a second. But this whole work energy picture, now remember, it is a new picture. I mean, it's newer than the force acceleration picture. And it's a different way of looking at the physical world. It is a work and energy. It's all consistent with force and acceleration. It all comes from force and acceleration, but it's a different way to look at the world, and it's useful in circumstances where the other way like isn't useful. So, and yes, in this way of looking at the world, what I'm specifically saying is to do work is to change the position of another object. It is to interact with a second object and change its position. That's what it means to do work. You could have the ability to do that for various reasons, but the most straightforward reason that we see right now, the primary, most straightforward reason that anything could have the ability to change the position of something else, to move something else, is if it itself were moving. So yeah, kinetic energy is the ability to move something else because you yourself are moving. The more 1F mv squared you have, the more you can F dx something else. And yes, indeed, when you F dx something else, when you do work on something else, you have indeed transferred some of your ability to the other thing. I mean, exactly what Claudia is saying. It sounds abstract and strange, but you literally are transferring your ability to something else when you do work on it. And why? Okay, I'll say this. It's funny. Like literally, as I was saying this, my wife was just moving a super heavy box across the floor. And if I were a good husband, I would have stopped and I would have transferred some of my ability to her box. But I'm a bad, but I didn't. Because I'm sure it was a Valentine's present for me. No, when you do work on something else, you're literally transferring an ability, because when you do work, because of Newton's third law, when you exert a force on something else and change its motion, like speed it up or slow it down, then you yourself do slow down, or depends if you're doing positive work or negative work. But like if you push something, if you're a billiard ball and you slam into another billiard ball, and so you speed up the second billiard ball, you yourself have now slowed down in the process. Your energy got lost if the other thing gained energy, and therefore you now have less ability to do that again the next time. Absolutely true. Okay, I'm over. Excuse me. I've gotten to the point where I went to a doctor and they were like, so do you cough all the time? And I'm like, no, I only cough when I talk a lot. And then I'm like, oh yeah, so I cough all the time, I guess. All right. So I hope that answered Claudia's second question. Let me know if it didn't. But now, here comes really the answer to her first. And all of what I'm doing here, if you're lost in the curriculum, this is all, you'll see in a minute. This is all about question 4 and 5. We already got the answers so you wouldn't feel lost. But what I'm really trying to, but if you remember on the blackboard or the whiteboard, how we did question 4 and 5, we set up this whole thing of total mechanical energy is conserved. We set up this whole thing of kinetic energy plus potential energy must be a constant. What I'm trying to do now, what I've just developed is what I meant by kinetic energy. In theory, that's what I just explained. Now I want to explain what I mean by potential energy. That is something that has not been explained on the board yet. Once I explain that, then I'll tie it back and show you, like, I'll tie it back. I'll repeat like the answers to question 4 and 5, and then we'll move on to question 6, 7, and 8. Like, again, just so you know, we're not. This is the reason that we spent so long on homework 1. Is homework 1B is meant to lay out all these concepts that I think we all do need to investigate deeply for the course. So again, forgive me if it's confusing, but we're still in homework 1B. We're still in the middle, and we're just using these questions like as a platform for expanding these concepts. That's what's going on. Okay. Oh, did it answer your second question? Your second question. Oh, good. Great. Thank you, Claudia. And then she just got points for closing the conversational loop. And I hope it's also clear, again, all those portals you can use more than once. Just get any points you ever can, anything to stay alive and hopeful. Okay, so now what I'm going to do. So now what I'm trying to move to is what the heck does this have to do with potential energy? Like, what the heck does this have to do with potential energy? So here's the deal. Okay. 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 Right. So now, so kinetic energy is not the only form of energy. Like, so the you being in motion is one way that you would have the ability to get something else in motion. But there's other reasons you might.
Any chance you could go back for a
Oh,
second,
sorry,
please?
absolutely. No, absolutely. I'll take a pause for a second. Let me know.
That's good. I got it. Thank you.
Thank you. And again, you know what I'm about to say, or at least Melina knows. Please note that what Melina just did when she asked me to go back, that's a portal for points. There's literally a portal that says, please go back. That is exactly intended for exactly that. She can literally, I know this is all ridiculous, but I'm just, again, whatever. It's life is a game, except that it's hard. There's a portal for what she just did. She can get points for that. And there's also a portal for please go forward, which takes a little bit more politeness. But if I start going down a rabbit hole, as I'm doing right now, you can always politely say, like, yeah, we get it. Can you please get back to the homework or whatever? And you get points for that too if you do it politely without like crushing my like spirit. But okay, so some, not all. What was I? Some, not all. Oh yeah, forces. Okay. So now, first I'm going to say, and I think I did say this last time, but I'm going to say there's just some forces are divided into two categories. For any given force is either known as conservative force or a non-conservative force. Now, first of all, I'm giving you a list just so you can like concretely picture what I'm talking about. Like examples of conservative forces include the gravitational force, like mg or gmm over r, like whether you're talking about gravity at the surface of the earth or in outer space, either one, both, they both are very relevant in this class. Either way, gravity is a conservative force. The elastic force, i.e. the spring force, i.e. Hooke's law, the thing that this course is like super based on, is a conservative force. The electrostatic force, which ends up being a big part of this course, doesn't come into like the second part of the semester, but ends up being like a huge thing in our life, like electricity, okay? Also a conservative force. Now, any of those forces on the left side of these columns, if they're conservative at all, they're totally conservative. Like this is like an on-off switch thing. A force like either is fully conservative, like, or it isn't. Okay, so the other forces like tension, friction, normal, like contact forces, so to speak. Or let me put it, well, yeah, whatever. The other forces are not conservative. Now, I'm just telling you that, where I told you that last week. Now I got to go deeper though and tell you like sort of why, like what, how do we know why a certain force is conservative or not? And like, who cares? What do we do with that information? That's what I'm going to get to now. Okay, first note, I mean, I'm ramping up this. First, on an informal level, I may have mentioned this last week, probably did. One thing that seems to identify the conservative forces is that any one of those that we name, like there tends to be an equilibrium or preferred state or orientation or position or arrangement associated with each one of those. In other words, like in simple terms, gravity is always trying to bring you to the ground, right? Like just that. Gravity is always trying to bring you to the ground. When you're not at the ground, if no other forces are acting on you, like you move, but or you accelerate. Once you're at the ground, then you don't accelerate anymore. Same thing with springs, right? Like the end of the spring always wants to be at a certain spot. And if you're on the left of it, you get pulled to the right. If you're on the right of it, you get pulled to the left, right? And ultimately, same thing with electrostatics, even though we haven't discussed that yet in this class, like electrons want to be closer to protons, just like bricks want to be closer to the earth, right? So informally, the way to recognize a conservative force is to if there seems to be a preferred or equilibrium orientation associated with that force, then that's probably a good sign that it's a conservative force. But that's not good enough for us. I mean, that is informally true, but formally, excuse me, rigorously, what are we saying? Here's what we're saying. Formally. Excuse me, sorry. Really very attractive. Okay, here finally comes. She only had to wait for an hour. Here now really comes the answer to Claudia's question. Let's remember now what Claudia asked an hour ago was what's the deal with that circle on the integral sign? Now, let me tell you, one of the reasons I'm taking so long to answer it is it's such a good question because it's not like Claudia just missed something. It's not like a symbol that like I explained last week and like she forgot or so. Like it's a symbol you've never seen before, or well, certainly you've never seen in a science class, I don't think. And for most, and it's not expected that you ever saw it in a math class before. Let me be very clear. I'm not assuming that any of you knows this symbol. Maybe if by accident you do, that's great. But I believe that part of the purpose of this class is to teach you the very important and big idea behind this symbol. So taking a long time, because so to be frank, like even if Claudia hadn't asked that, like I would have to be making a very big deal of this. This is new information. This is calculus information that you're not expected to have already had. You're expected to have taken enough calculus that you can like handle it or like be with me when I teach you this bit of calculus. Okay. I'm saying that like, because I've had this issue before, like, please, so bear with me. So that don't get intimidated. In other words, and don't think, oh my God, this is like more calculus that I have to review that I don't. No, this is new. So what it is this. Well, so first of all, I'm saying for me, I'm about to do a thing. I'm about to make a definition where I'm going to define conservative forces in a calculus way. So first of all, I'm just saying at the top of this page, like from now on, if I put F with a subscript C, I just mean specifically conservative force. Okay, that's just like notation. So if you ever see F sub C, it means some conservative force. Okay, fine. So that's physics. Now what I'm saying is, as far as integrals, and again, I'm here to say we need integrals for this class. We need to learn integrals for this class. The best way to learn them to the level that we need for this class is for you to know that I know that many of you still might not or should not feel totally confident with them. Everything I ever say about integrals is not in the assumption that you've already mastered them. It's in the assumption of we should be humble before integrals. We should assume that they're hard. They are, but we still all have a big chance and a big motivation to get our minds around them. Okay. The integrals are not ahead of you. They're to the side of you and you're trying to embrace them. So what I'm going to believe here is that you've seen integrals and you know in some part of your mind that there's two types of integrals already, like in your life, like, right? There's indefinite integrals and there's definite integrals, right? Like indefinite integrals are the ones that don't have boundaries on them. Indefinite integrals are the one that just say like F, like integral sign f of x dx or whatever. And with indefinite integrals, in other words, you're performing the continuous sum of products, like you're doing the area under the curve, however you like to think of it, but you don't know exactly from where to where, right? When it's an indefinite integral, you're just being asked to analyze a function in general terms. And what you get as your answer is a function in general terms. Like you don't get a numerical answer. You don't. Right? And so your answer you get for indefinite integrals ends up always having a plus C at the end of it. We're going to go back and like talk about that in physics terms and stuff at some point. But that's indefinite integrals. You always get the plus C, right? And again, I'm hoping that what some of you are thinking is something like, well, I was never like totally comfortable with that, but yes, I know what he's talking about. Like, that's where I want you to be. Like, you're familiar with what I'm talking about, even if you've never felt 100% on top of it. That's indefinite integrals. But then definite integrals means you're literally applying the function. Like you're not just doing area under a curve, like in general, you're specifically going area under, you're given a curve and you're trying to get the area under it specifically from over here on the x-axis to over there on the x-axis, right? So you're going to get a function and then you're going to evaluate that function. You're going to plug in values for the x or for the independent variable, like there and there, and subtract and get an actual answer, right? That's for definite integrals. In fact, forgive me, but let me expand on that for one more sentence. Please note and this is an example saying, I'm not going to write it down because I don't want to rabbit hole myself, but you may want to write this down if it's never occurred to you. Functions are number in, number out, right? A function is a black box. You stick a number in, and then the black box applies a rule or a mapping, and then some other number comes out, right? That's what a function is. Number in, number out. An operation, in contrast, so please write this down if this is never fully sunk in with you. And again, like everything else, I took 50 calculus classes before this sunk in with me. A function is number in, number out. An operation is function in, function out. And whenever we take a derivative or an integral, when we differentiate or integrate, we're performing operations, not functions. Let me say that again. Derivatives and integrals are not functions. They are operations. What does that mean? It means that the derivative and or the integral takes a function in and spits a function out. Right? When you integrate a function like force with respect to displacement, what you get out is a function like work. If it's an indefinite integral, you just get that, a function. It's just a rule, like you spat in y equals 3x squared. What you get out is dy dx equals 6x, or the other way around, right? Or integral, right? You just get another rule. Only when it's a definite integral do you then evaluate and plug in values for x so that the rule gets applied and spits out a final value for y, right? When you evaluate a function, that's what's happening. You've taken in a function into an operation. The function came out. Now you just have a raw function sitting there. If you're lucky enough for it to be a definite integral, then what basically someone's telling you is, now I got a couple of values of x here that you could plug in. So plug them in, and then you'll get an actual value for y, right? It's another step. Why am I saying so? First of all, that's what's happening when you evaluate a definite function. You're then using the function to get a number. Or in science class, in physics class, to get a measurement, to get an actual number of joules, or whatever the case may be. Now, it turns out, you know about indefinite integrals, definite integrals, but it turns out there's this other special kind of integral that's a real thing in math. I'm not making this up, and physics didn't make this up. This is a math notation where if you put a circle, okay, fine, hour and 12 minutes from Claudia's question. When you put a circle, when any mathematician or physicist puts a circle on an integral, what that means is they're now talking about a special kind of integral called a closed integral. A closed integral. And what a closed integral is, in general, is a definite integral, i.e. one that has boundaries, that's going to ultimately spit out an actual evaluated numerical answer. But a closed integral is special in that even though it is definite, we don't see boundaries on it. We don't see x equals 1 or x equals 2 or whatever, because closed means just that. It means closed. It means closed path. It means that wherever you start as your first boundary, you come back to an end at that same boundary. It means an integral around a round trip, always. So specific, and I'm going to show you how that works in a minute, obviously. But so first of all, this is a math point I'm making. A closed integral is a specific type of definite integral for which the two boundaries, the two limits of integration are the same, that you end up where you start. So you do get an answer, but it doesn't actually, but you don't have to specify where you started or where you ended, because as you just, you could start at x equals 1 and go back to x equals 1, or you could start at x equals 3 and go back to x equals 3. No matter what, as long as you end at the same place, it's called a closed integral. So now what that means, and again, it's going to come up a lot in this class. Okay, on the next, I'm gonna pause for a second because this is important to write down. I'm gonna write it a different way, sort of more in English or physics terms on the next page. But this is a highly, you see why, again, in a way why I took so long to build this up and said so many different like English and informal things first is by the time we land at this notion, this is a very formal, like it's a very mathematically technical and maybe even esoteric definition. Like what I'm ultimately saying here, well, first of all, by the way, notation, whenever I write IFF, if I ever write IFF, that's like not a typo. I mean if and only if, for what it's, it's like a stronger version of if you care. But what I'm writing here is ultimately the definition of a conservative force is this: a conservative force is a force for which the closed path integral of that force is necessarily, like always, zero. So again, I have a triple equal sign in there because I'm saying, like, I don't mean just like if by coincidence occasionally you can get the answer zero. I mean if for however reason, if you know in advance that no matter what you do with this certain force, no matter how you do it, that if you take a round trip, well, this is what I'm going to write in English in a second. But okay, so mathematically, I'm saying if you know for a fact that the integral of this particular force will always return zero as long as you start and end in the same position in space with this force, then we call this force a conservative force. That's the definition. So the definition of a conservative force, strictly speaking, is a mathematical definition. It is a force for which the closed path integral is always zero. So in order to understand that, you got to understand path integrals, and you got to understand now this new thing of closed path integrals. Now, of course, I'm going to turn this into English in a second. I'm going to try to make this more concrete, but that is that's that. So that's a double answer to Claudia's question. So okay, just to summarize again. First of all, from here on in, whenever you see a circle on an integral of any kind of integral in physics or math, and I think it'll come up in PChem, for example, it certainly comes up in Calc 3 all over the place if you have any reason for taking Calc 3. I mean, I love Calc 3, but like whatever. But and it comes up in PChem. I can't remember instrumental if it comes up, but definitely comes up in. So if you ever see a circle on an integral, it means the closed integral, the definite integral from a place back to that place. That's what it means. And the utility of it here in our class is if the closed path and remember again, also, like there's all kinds of integrals in the world, and any of them could be closed. But now in this class, we're specifically talking about path integrals, right? In other words, we're talking about integrals with respect to space. There are other integrals too. Like you could have the integral of force times dt times time. That's a thing. It's very real mathematically and physically, but it's not what we're talking about here. Here, we're talking about path integrals. We're talking about integral of force with respect to space. And if the closed path integral of a force equals zero always, then we call that force conservative. Like, so that's my answer to Claudia's question. Now, who cares? Like, what does this have to do with potential energy or the spring or any? Oh, okay. I'm just looking at the chat. So that's what I have to tell you now. I'm going to put this in English now. Then I will pause and see. I mean, it doesn't look like anything's happening in the chat, but there's certainly, it certainly wouldn't shock me if there were. Okay, so wait. So this is the mathematical definition of a conservative force in English or physics terms. Okay. Okay. So looking at the chat, looking at the time. Okay, okay. Okay. Oh yeah, and by the way, also, sorry, quickly, just a little break off. Also, like for people who don't know, there's also a portal for like what Eric is doing and what I think Matthew's doing, although it's not 100% clear to me, and what Claudia is doing. Like, just so you know, even showing an avatar, I can never pronounce that word. Just showing like a picture in your black box, like when you're not showing video, if you show anything at all that isn't just your name, any kind of picture, anything that just breaks up the monotony and helps me identify you, there's a portal for that and it's called Avatar, and you can screenshot and you get points for that, just so you know. So like, thank you, Eric. Thank you. And also all this stuff, just also, I'm hoping too, as many disadvantages as there are to Zoom, like I'm also hoping that since you guys, since we know each other since you put in the effort to come to physical class at 8 in the morning last week and the week before, I'm also hoping that it makes it easier for us to interact. Like, what I'm saying is, I do know who you are and you know who I am. So please feel free to like just interject at any time during the Zoom class today. I know realistically that you're all going in and out. I get that. And I know and please believe me, it's easier to be me than to be you. Well, you know this, but like I'm talking, so I'm keeping myself awake. So the time flies a little bit more for me, but I know from experience, if I'm just sitting here listening, it is so torturous, right? So please, anything you do, just like if you get the impulse at all, any of you, all of you, at any point, you can interject, even if it's like slightly, even if you think it's like from 20 minutes ago or something, just if for no other reason to keep yourself awake and owning the class more. Okay, like nothing will be considered stupid or shameful here. Okay, anyway, I'm just saying that because I just got reminded because I see the avatars and I appreciate that. It just helps. Okay. So now what I've now done is given a definition of a conservative force. We're almost like back again. Where is this going? Why am I talking about this? This is not a tangent. This is the material, but it doesn't feel that way probably. The reason I'm talking about conservative forces is ultimately it's conservative forces and conservative forces only that store potential energy. Okay. Like that's where this is heading, is that I need to do, but also I need this, you need this for later in the course for circuits. I mean, to be blunt, like you can't understand circuits unless you can understand this like closed loop business or closed path business. But so where this is heading is I'm about to, in 2 minutes, tell you that that what potential energy has to do with is work being done by conservative forces and only by conservative forces. Okay, that's where this is heading. But I have to do one more little interlude to get there. Um, okay. So I want to do a quick interlude here. It's not an interlude, but let me give you an example because it's like it's all a bit abstract, right? So let me give you an example of how this definition plays out and creates the list that we have where we say, for example, gravity and springs are conservative, whereas like friction and tension are not conservative. Like like, why, how are we saying that based on this like weird integral definition? Well, here's how. It's all really, in a big way, comes down to minus signs, strangely enough. It really comes down to minus signs. Here's what I mean. And I'm just going to talk this now. Like you can write this down however you want. But the summary is, if you really think about the role of minus signs in the case of gravity versus the case of friction, you'll see how this definition plays out. So here it is. With gravity, I throw something up. Right. With gravity, I send something on a round trip. Like I'm going to send something on a closed path and consider the closed path integral. So I send something on a round trip. I throw something up and it comes back down to where, like I throw it up like from height 0, it goes up to height h and comes back down to height 0. So it's gone on a round trip, right? So if I consider the work that gravity does onto this object, this cough drop, throughout the entire round trip, let me consider, in other words, the integral of the force of gravity with respect to dx, like so the f dx integral of gravity on this thing from like y. So it's like the integral of, so the integral of f dx, what does that mean? The integral of mg, like the force here is mg, times dx. Well, what's x? Like let dx is displacement, is path. Well, in this case, it's a vertical path. So we'll call it dy if you like, right? Because it's like going up and down. So it's like the integral of mg dy from y equals 0 up to y equals h, back down to y equals 0. Closed path integral. Okay. Now again, I'm doing this. You might want to. I'm just talking this. You might want to write it down in your way. But if we consider that closed path integral, oh yeah, like how do you do a closed path integral? One thing I meant to write down, like to do in general a closed path integral. Like how do you even do it? Well, just to be explicit mathematically again, when we say closed path integral, we mean from here out to somewhere and back to here, right? So the way to do the math, or the way to think about the math, is do the integral from here to there, and then do the integral from there to here and add them together, right? In other words, a round trip just is the sum of an out trip and an in trip. Just, okay, so that's what I'm going to do in my head here with gravity. We do the integral out. We do the work that gravity is doing on the way up. Well, on the way up, we're traveling up. So our displacement is like from 0 to like h, right? Our displacement, let's say, is positive, is up. The force of gravity is down, so it's negative, right? So on the way up, it's the integral of negative mg dy, right? Now, mg happens to be a constant, so it comes out of the integral. Oh, sorry. Oh, Melita, yeah. Sorry.
I just wanted to ask, so if like we write it as like the plus sign, like instead of writing it as one of the same, like is that equivalent? Like, would that be okay?
Wait, so I missed it. If you write it, sorry, say that again.
If we write it with the plus sign instead of writing it with the like the 0,
oh,
would
yeah,
that be okay?
yes, it's definitely 100% equivalent. As long as you have your limits, you notice I'm like being careful with my limits. Like I'm literally saying like from a place to a place, but then literally like plus.
That place to that place.
Right,
Okay.
exactly. Yes, exactly. So as long as you do that, yes, they're equivalent. They're totally equivalent. It's just the circle is a way of then avoiding having to specify. The circle is a way of saying it didn't even matter. Okay, yeah, I guess here's the one subtle, slight way in which they're not equivalent. As long as you know that those x1 and x2 are like totally arbitrary, that like no matter which ones you picked, it was still going to work out as long as you came back to where you started. Then yeah, it's totally equivalent. Right? Yes. It's just the circle is just trying.
Oh,
Oh, sorry. Go. You go. Sorry.
no. I was just thinking, yeah.
Okay. All right. So yeah, no, good question. Right. So yeah, you could write it either way. Bottom line is we're talking about round trip. So, and here's the real test, if it makes sense. And I'm not saying we're gonna have to, like a lot of times we can sort of do these in our head or well, I don't know if we can, but I'm going to right now. Like you all, whether it's Melita or Claudia or anybody, is going to stop me. I'm about to do this like in my head. You really have to be honest with me, any of you, and you could be in the direct chat. Tell me if I lose you in what I'm about to say in English. This is what I want to say. With gravity, especially because gravity, call it mg, is a constant and it comes out of the integral. What I believe therefore, the integral is like negative mg integral of y equals 0 to y equals h of dy, right? Integral of dy is just y. So it's y evaluated from y equals 0 to y equals h. Like I should be writing this down, but I'm not. So you get, so on the way up, the work done by gravity is negative mg y evaluated from y equals 0 to y equals h, right? So that means mg h minus mg 0, right? So you really get, at the end of the day, for the work done on the way up, you get negative MGH. Let me pause for a second. I'm saying two things right now. One, just in terms of practice for integrals, the integral on the way up for the work done by gravity, on the way up from a height 0 to a height h, I'm claiming you get negative MGH. Number one, hopefully you either wrote down or you could see how I got that doing the integral practice. Number two, to take us, and I will look in the chat in 1 second. Like, I think it's important that we're all together on this. But number two, it's like practice doing integrals because it's not meant to be a super hard or crazy integral. It's just, I just mean the integral all the way up. But number two, hopefully you recognize the result. Oh, some of you, I think, recognize the result at this point. Like I am just claiming the work done by gravity on an object on its way up from height equals 0 to height h on its way up. Like why on its way up? Because I threw it. Like it's moving up, but I'm taught. So, but there's nobody forcing it up. I just gave it an initial velocity. I just threw it. So it's like, it's going up on its own steam. And I'm calculating the work done by gravity. I'm claiming that the work done by gravity is negative mgh. Mgh, because in short, simple terms, mg is the force, h is the displacement, and the force is constant. So it's mg times h. That is the work done by gravity. I do believe we also said last semester that no matter what crazy path you take or whatever, to get from some low height to some high height, the work done by gravity definitely always from that integral we just did is mgh. But I'm also claiming, here's where I'm going to pause in a second. I'm claiming that on the way up, the work is negative MGH, and I don't care how you define. I'm assuming that I'm defining up as positive and I'm defining down as negative. But frankly, even if you made a different choice, even if you define down as positive and up as negative, you're still going to get that the work done is negative MGH because definitely when you're on your way up, you're displacing in one direction, but the force is in the opposite direction. This is the key. The force is against you. No matter how you define your coordinate system, the force is in the opposite direction from the displacement. Therefore, I'm saying that on the way up, the work done by gravity is negative. It's negative. What does that mean in English? Back to like Claudia's other question. It means gravity is like working against you. It's doing negative work. It's taking energy away from you. It is slowing you down. Hence, on your way up, of course, you're slowing down. You're losing kinetic energy. You're eventually going to stop. All I'm saying so far is on the way up, the work done by gravity is negative mgh. Wait, first I'm gonna pause. Now I'm not done. Well, I'm not done with anything yet, but I'm pausing for a second just to see. Are we cool on that so far? That on the way up, I'm just gonna sue Jonathan's cool. Okay, and Melita's cool. Okay, so on the way up, the work done is negative mgh. Now you start falling down to complete your round trip, right? I'm analyzing a round trip. It all seems, hopefully, I'm making a big deal of it because I'm trying to make a contrast here. On your way down, all the same math, all the same logic, except now you're on your way down. Gravity is pulling down. You are displacing down. So no matter how you define your coordinate system, the displacement and the force are in the same direction. It's either a positive times a positive or it's a negative times a negative. Either way, you get a positive. So on the way down, your force is, your work done is positive mgh on your way down. So now I say, okay, okay, for gravity, gravity always wants to bring you to the ground, right? It always wants to bring you down, yo. It always wants to bring you down. So when you're going on your way up, the work done by gravity is negative. It's sucking kinetic energy out of you, slowing you down. Then you start coming back down to where you started. Now gravity is doing positive work on you, giving you kinetic energy, right? And by the end, necessarily, in the case of gravity, since gravity never flipped its vector, it was always pointing down, whereas your displacement did necessarily flip for this round trip. At the end of the day, gravity did zero work on you for that round trip. And if you step back, and especially if you think about it like the way Melita was, or the way Jonathan's face was, you could see like it doesn't really matter what I picked as my zero or what I picked as my H, as long as I went out somewhere and then came back. In the case of gravity, whatever amount of speed it sucked out of me on the way up, it necessarily gave back to me on the way down. So gravity necessarily did no work on me for that round trip. That precisely, exactly, is why we call gravity a conservative force. It's really because its negative sign is always sitting there because of that equilibrium that it's always trying to bring you to. It's always bringing you down, whether you're going up or going down. So the negative signs like work themselves out and cancel themselves out in this convenient way that at the end of the day, gravity neither gives nor takes away anything for a round trip. Now, all of that, to me, my mind, makes so much sense. To my mind, and now that I thought about it, it makes so much sense that I'm almost left. A lot of students often are left feeling like, well, that makes so much sense. Like, doesn't that, obviously, doesn't that work that way for all forces then? Like, it seems so airtight, the logic. Like, how could it possibly ever not work? Good question. So, at the risk of boring anybody or leaving anybody, whatever, at the risk of boring anybody, let me somewhat quickerly talk about what friction would do. Friction wouldn't do this. Hopefully I'll be quicker with this, but whereas with, for example, friction, consider round trip closed. Okay. Now, somewhat quickly, and by the way, remember, round trip is like the English or physics version of saying closed path. Closed path is the mathematical way of saying it. Round trip is the English way of saying it. Same point though. When you end up at the same place you started in space, That's what we mean by a closed path. So now with friction, if I have a box on a table, on a rough table, and I start moving the box to the right. Now, I might be moving the box to the right. I'm not looking at that though. Let's look at I mean, I could look at that. The answers will end up being the same thing, but I'm looking at friction now. As I'm moving the box to the right, look at the force of friction exerted by the table, the rough surface, onto the box. Say the box moves a displacement of X to the right, and the force of friction, mu times the normal, like the magnitude is some number of newtons. While I'm moving the box to the right, friction, of course, points to the left. It like slows down the box. It opposes the box's motion because it's friction, right? So if I move the box a total displacement of X, while the force of friction is F, lowercase f, the displacement is in one direction, the force is in the other. So they multiply together, and it's a negative times a positive no matter what. So you get negative work, right? On the way out, friction is doing negative work on the box, slowing it, taking away kinetic energy, slowing it down. And that's just like gravity on the way up. But then the key point is, when I then stop the box, when I turn around the box and start bringing it back to complete the round trip. Now, granted, my hand is the one doing that, but if I'm looking at the work done by friction, now when the box is coming back in, now the box is going to the left, not to the right, but now friction also flips its direction. That's the key and entire point. It's like so dumb and simple in a way, but it's so different. Friction flips. Gravity never did. Gravity was always pulling me down to an equilibrium place known as the ground. Friction was never pulling me toward any particular place. Friction was always just opposing my motion. So when I was going out, friction was pulling in, pushing in. And when I'm coming back in, friction is pushing out. So both times, the work done by friction is negative. This is the key, right? So the total work done by friction for a round trip would not be zero. It would be literally like negative 2F times X. Whatever, X being that displacement. And I say 2 because one out, one in, and I say negative because it's negative each time, right? No matter how you slice it. And if you want to look at, if you're like, yeah, but in there, that's weird because, your hand had to be doing something the whole time. Sure. If you want to look at the work done by my hand, by either my hand is pulling some rope with tension or my hand is pushing with a normal force, whatever my hand is doing, it's doing positive work. On the way out, it's exerting a force to the right while the thing displaces to the right. But then on the way in, the hand also has to flip. So on the way in, it's all positive. So friction does double negative. My hand does double positive. They are non-concerned. So in other words, friction takes away a net amount of energy when the whole round trip is done. Friction has taken away a lot of energy. And that's why the table gets heated up a lot. The table gets heated up on the way out and gets heated up even more on the way back in. You see what I'm saying? And with my hand is doing positive work, not negative work, but it just accumulates and accumulates. So my hand gets more and more tired. There's no return for its value. Okay, so bottom line, if you think everything I just said just has to do with like minus signs and how they play out, you're right. It does. But at the end of the day, it means there are certain forces that do no work, a net amount of zero work over a round trip guaranteed. And all the logic I just said about gravity, the whole logic of it absolutely applies to springs as well. Like when the spring is, when you pull the spring out to the right of equilibrium, the spring is pulling to the left, but then you let it go and the spring is still pulling to the left to bring it back in, but now the thing is displacing to the left. I mean, it's just like gravity, right? So springs and gravity return what they take away, and vice versa. Therefore, and again, stop me any time. So what we do with conservative forces, because with conservative forces, we know in advance this fact about round trips, we have a technique or a trick really for saving ourselves computational hassle. We say, only with regard to conservative forces from now on, we say that any trip that we watch, any path, if we watch an object get displaced, if we know for a fact that all the forces acting on the object, if we know for a fact that all the objects, if we know for a fact that all the forces doing work on the object are these kinds of conservative forces, then we have this trick. What we say is, you know what? If we watch an object undergo a journey of any kind, a path, like from here to there, we say to ourselves, you know what? We can treat that trip. We can always treat that trip as the outward bound leg of some round trip. Like, even if it's not going to do the inbound leg, even if we don't see it do the inbound leg, we can, any trip that anything takes, we could say, imagine that that's just the outward, the first half, the first leg of what would eventually be a closed path. We know exactly what's going to happen on the inward bound path, like on the return trip of that closed path. We know that any amount of energy, any kinetic energy that this thing loses on its way out from equilibrium is precisely the amount of kinetic energy that it's going to gain on the way back to equilibrium. For example, if I bring something up to a high height of h, right? I bring something up to a high height of h and I hold it there. So something is sitting here at a height of h. It's sitting here. So it has no kinetic energy at all, right? So it seems like it has no ability to do work. But the thing is, I know how much work I did to get it to this height h. I know gravity did negative mgh, so I had to do positive mgh to get it here. I did work mgh to get this thing here. And then it seems like the energy is gone because now the thing is sitting here. So I did all this work. I gave it all this kinetic energy. Like I was bringing it, and then it stopped. So it seems like all this energy, mgh worth, is gone. But the thing is, if I drop this, or when it drops and goes back to a height of 0, I know already in advance, I already know that the total amount of kinetic energy it will have by the time it hits the ground the total amount of 1/2 mv squared it will have is exactly the mgh that I gave it to bring it here, right? It's exactly the amount of mgh that gravity took away from it to get it here. I know with gravity that gravity will give back. By the time this thing gets back to the ground, gravity will give back everything that gravity took away on its journey up to here. So I can say, oh, even though this thing isn't moving, it's in a position, it's displaced from its equilibrium by an amount that allows me to know exactly how much energy will return to it when it returns to equilibrium. And it is exactly the amount of work that I did to get it here. So I can say it's storing that energy. I could say, even though this thing isn't moving, it is in a weird place. It's in an unstable place. It's under the presence of a conservative force. So I know by the time it gets back to equilibrium exactly how much kinetic energy it'll gain. So I'm going to say right now that even though it doesn't have that kinetic energy yet, I can predict it with such reliability that I'm going to say right now this thing is storing that energy in the form of potential. Now, again, notice I could not say anything like this if we were talking about friction or tension or the normal force. This only applies to conservative forces, only applies to forces where the total amount of work they do is 0 over a closed path. But if it is that kind of force, then I know for any path I undergo, I could just treat it as the outward bound leg of a closed path. So that's what we do from now on. We just to save ourselves a lot of computation, we say from now on, you could have energy because you're already moving, or as long as you're sitting still in an unstable place under the presence of purely conservative forces, even if you're not moving yet, we know what will happen when you move and where you'll move to and how much energy you'll gain. So we're going to say that the amount of energy it took to get you to this unstable place is exactly the amount of energy you'll gain back when you get to the stable place again. And so we're going to call that potential energy or stored energy. Where is the energy stored? Is it stored in the object or in the earth or in the system? I'd say it's stored in our minds. It's stored in our memory. It's stored in our predictive power. Like, we don't literally have to believe in this. We could just do out all the calculations and just do everything in terms of kinetic energy every time. But it's so much easier and straightforward just to say in advance, oh, we already know in advance that the energy is being stored in our minds until the object gets back to equilibrium. So therefore, what I'm saying is thus. From now on, we're going to define the change in potential energy, the gain in potential energy, to be the amount of work that a conservative force would do to bring you back, to bring a system or an object back from some spot, whatever spot, X naught, some spot, to equilibrium. Like, see, this is like a funny trick. Notice there's no, now, again, this is all back to the Claudia thing, right? And like the everybody thing. Notice I'm not putting the circle on the integral now. I put the circle on the integral to define conservative forces. I'm saying what a conservative force is a force which does no work over a closed path. Once we know we're dealing with such a force, we can say from now on, whatever amount of work that conservative force would do to bring you from so what I'm saying in English at the end of the day, what is potential? Like, remember, what is kinetic energy? What is kinetic energy gained? What is the transfer of kinetic energy? It's the work done on a system from one place to another. Like, when you do work on a system to move it from one place to another, you give that system kinetic energy. And it's like a gain, it's a change, right? Like the work you do transfers kinetic energy. The system gains kinetic energy. If you do positive work, the system that you did the work on gains kinetic energy and you lose that kinetic energy. It's a transfer. Potential energy is now a transfer as well. The potential energy that a system gains is the amount of work done on it by a conservative force in order to restore it to equilibrium. So it's potential in the sense that it doesn't have to have happened already. It's a prediction. When something's not at equilibrium, it took work. So you could put it another way too. And I should say, I'm not going to write it down because I think it confuses some people. If you ever look this up on websites or textbooks, oh, is that a hand? Oh, that's my hand. It's so weird. Sorry. If you look potential energy up in textbooks or online, oh, is Shawnee in this class? No, Shawnee's in another. Okay. If you ever look this up, it will often define it with the limits of integration reversed and with a negative sign. Don't let that confuse you. What a lot of people will say, and this is also true, I just find it less straightforward, but a lot of people will say what potential energy is the amount of work that you have to do on a system to get it away from equilibrium. And that's true. What we're saying here is they're one and the same thing. As long as the only forces doing work are conservative, I'm saying potential energy is yes, it's the amount of work you did to bring a system away from equilibrium. And what that equivalently is, predictively, is the amount of work that the system would, sorry, that's the amount of work that the conservative force will do to bring the system back to equilibrium. We know it in advance if it's a conservative force. So potential energy is the work done by the conservative force to bring a system from some arbitrary spot where it's like sitting there unstably to the equilibrium spot of x equals 0. Okay, we are almost done. I mean, but both with what I wanted to do almost. And I'm going to keep my promise. Like, you're not having a break, but I'm watching the clock. Technically, class ends at 10:40. I will end no later than 10:30. I know it's not like hugely generous. I mean, it's not generous, but no later than 10:30. But if I do get through what I'm trying to get through, if I could get, I at least want to get to question 6 so that we're back onto the homework sheet and you don't feel but if I could get to that by 10 earlier, then I'll let you go earlier. Okay. I'm not like trying to hold you mercilessly. But so we're almost there. So this is what potential energy is. Now I'm going to apply it to a spring. So you see where that came from and how it applied to questions 4 and 5. Okay, but and again, please and don't not stop me just because you want to go. I mean, whatever. Stop me if you have any questions. I'm looking at the chat. Okay, so the question is, so I've said all of this abstract stuff. So what does this all have to do with a spring? Oh, wait, 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 sorry. Yes, that is the question, but I apologize. We'll go back one page. There's one more thing I have to add. Oh, right, okay. Okay, just one thing, just again, to bring this back, like I said this last week, but I don't think I gave a reason really. Here's the what I'm saying now is, once you accept this idea of potential energy. Oh, and I could even, I'll even say one more, sorry. I'm gonna rearrange these pages in 1 second. Okay, let me just. Okay, you could tell me to flip around. I'm open to anybody asking, can I go back, or if I just, here's what I'm saying. The pages are now in a different order. I'm saying I'm saying potential energy is the work that the conservative force will do to restore a system to equilibrium. Like, it's a prediction. That's why it's called potential. Like, it doesn't have to have happened, but the fact that we know what will happen is what enables us to call it stored energy. So potential energy is the amount of work that a conservative force will do to restore a system to its equilibrium configuration. That's what potential energy is. Therefore, to relate it back to kinetic energy, therefore, and to relate it back to Claudia's other question, I'm saying, like, work is the transfer of energy. Work is how you move energy from one system to another. What energy is the ability to do that. Energy is the ability to do work, but you could have it for different reasons. The primary reason you could have energy is if you yourself are already moving. That's 1/2 mv squared. That's what we call kinetic energy. So kinetic energy was the ability to do work by virtue of motion. Now I'm saying potential energy is the ability to do work by virtue of configuration, orientation, position, like how things are arranged. If things are arranged unstably, if a system is not at equilibrium, then we can say, even if it's not moving, it has the potential to move. And if it did move, we would know exactly what was going to happen. So if something's not at equilibrium, and this is something that can occur, we don't even have that concept if we're not talking about conservative forces, right? Like, things under the presence of friction there's not even an equilibrium to discuss there. But if there is an equilibrium orientation that you can identify and the system's not at it, then whatever work would be done to bring it to equilibrium, we call that stored energy, potential energy, right? So now we have energy. You can have energy because you're already moving, or you could have energy because when you move, we know exactly what's going to happen. Either way, those are forms of energy. So now we say that in general, and those are the two only forms. That's the good news. Those are the only two forms in mechanics, which, like, right now we won't be for the rest of this course. Like in other words, electricity doesn't count as mechanics. But if you're in mechanics, or whatever, if you're in classical physics, the only two types of energies you could, or anyway, the only two types of energy you could have are kinetic or potential. So we say from now on, your total mechanical energy that a system has at any one given spot, at any one given place. This is all about space we're talking about here. Notice again, everything we're talking about now, excuse me, is with respect to space. Last semester, it really was all with respect to time. Now it's all with respect to space. Like, that is a subtle but important distinction in, like, how we're thinking these days. But so the total amount of mechanical energy you have at a spot in space is the sum of all your kinetic and all your potential. And what we're going to claim now is as long as all the forces doing work on you are conservative, the whole purpose of this potential energy construct is now we can say, like, here's the point, is even though this is all coming back to the idea of work, where did the energy come from? Work. Why do we care about the energy? Because it could do work. But now that we have a concept of potential energy, we can sort of skip the work step in a lot of our calculations. That's like really what's going on here, or the many steps of work. And we just say from now on, whenever we're looking at a system, if the only forces doing work on it are conservative, such as there's only spring forces doing work, or springs and gravity, but there's no friction and there's no tension, if that's the case, we look at any one spot and we say all the kinetic right here plus all the potential right here accounts for everything. Like however fast it's moving right now and wherever it is, together, those are the only reasons that this thing ever could do work. So if we add up all the kinetic and all the potential, that's the total energy. And that total amount will not change from spot to spot, because that's the whole idea that this is coming from, is over a closed path. The total amount of work is zero, right? So from here on in, whenever we're anywhere within a closed path, wherever we're in any kind of trip away or toward an equilibrium, all we're viewing from now on, we're saying you might think you're losing kinetic energy, like something goes up away from the table. I threw it up. It looks like it's losing energy. It is losing kinetic energy, but we can say every bit of kinetic energy it's losing, it's storing as potential, and vice versa. When it's coming down, it's losing that potential, but it's getting it back as kinetic. So this all goes back to the 6th grade now, like where the whole idea of stored energy is we really do now, it allows us to think in one-to-one correspondence. Any bit that you ever lose of kinetic, you're gaining as potential, and vice versa. So your total amount of kinetic and potential at any one given spot is the same at all spots. That's what we were saying last week. That's what I feel like we've now justified or explained. Hopefully, again, of course, you could still ask questions, but at least now I feel like it's there for the consideration. Like we haven't skipped any steps. And now only that thing that's left to do in a maximum of 20 minutes is apply this to the spring, right? Okay, so now this page, let's get back to questions 4 and 5 of homework 1B. How does any of this apply? But I mean, how are we going to apply this EX1 equals EX2 thing, mechanical energy conservation? How are we going to apply that to a spring? Well, we must, hello, okay. Compute the potential energy function so what I have to do now is compute what is the potential energy due to a spring. Like in a like in the quick example I gave like an hour ago about gravity, I did out the integral in the air in my head and came to the conclusion that if you do the integral, the work done by gravity is with plus or minus signs depending on direction is mgh, right? So ultimately if that was the work done by gravity to restore you to equilibrium from a height h, then in effect what I was showing there is that the potential energy due to gravity is mgh. In other words, the potential energy due to stored by some conservative force is the amount of work that that conservative force would do to bring you to equilibrium. So it's different for every conservative force. For gravity, it's mgh. But what is it for a spring? I mean, once we know for all time, but it is different for each conservative force. We must, what is the work done by a spring to restore a mass from x equals x naught to x equals 0, right? That's the question. Like, if you're following all of what I'm saying today, in order to know the potential energy due to a spring, we need to calculate the work done, the work that a spring would do to bring an object, a mass, a particle, from x equals x naught back to x equals 0. Like, that's the definition of potential energy that we just spent all this time developing, right? Once I apply this definition to the force of a spring, I'll have the answer for springs for all time, but it'll just only apply to springs. So let's do it. Like, and again, you have the answer from the, but I only gave you the answer. I didn't tell you where it came from. Now I'm telling you where it came from. So the word, well, just happened. I don't know what just happened. I'm going to be very explicit here. I am watching the clock. So I don't know if it's going to be earlier than 10:30, but it will be no later than 10:30. I'm being careful here. So I'm calculating the work done by a spring to bring, oh yeah, sorry, Melita, yes.
Maybe you're gonna get to this, but I just wanted to ask, why is the work like a triple equal sign versus the negative kx is only a double?
No, that's a great question. That is a great question. Well, okay, so the work, it's particularly great. Okay, first of all, it's a great question because I do care about these whole triple equal sign things in general. But then also, you're right, it's particularly weird with the, okay, with the Hooke's law. So the work is a triple equal sign because I'm specifically saying that the definition of work is that integral. Like, I'm specifically saying triple equal sign there to,
Okay.
okay, yeah, and to distinguish, because otherwise I could say work double. I'm going to say this I know you get it. I'm going to continue answering anyway for the sake of everybody else because it really is an important question. If I say work double equal sign, then I'm talking about what work does, which is then when I would write like work double equal sign 1/2 mv squared minus 1/2 mv naught squared. Like, it really is a different equation, and I don't want to confuse people. Like, what work does is it changes kinetic energy, but what work is the integral of force with respect to displacement. So in general, to everybody, I'm using triple equal signs whenever I'm using a definition. Also, and this is also important, and I'm also glad Melita is asking, because generally speaking, when you do the 5-step method for solving these problems, especially on exams, when you're looking for step 3, the GDP, general definition or principle, that's a step that like I require that I think is super, super helpful, but it takes people getting used to. They don't always do it in other classes. A hint when you're looking for step 3, GDP, general definition principle, often what you're really looking for is some kind of triple equal sign statement. So I'm also like often trying to highlight those as like hints for like this could count as a GDP if you're like stuck in a problem at step 3, like maybe look at things that have triple equal signs in them. But now F equals negative KX. Melina's really right to ask, like, kind of like, why does that not have a triple equal sign? Here, the real technical answer why it doesn't is because F, which means force, F is not defined to be negative KX. Like, force means an interaction between two objects. Like, if anything, the definition of F is really Newton's third law. They're like where I push you and you push me back the same way. Like, the definition of a force is not negative KX. Put one final way, there's tons and tons of forces that aren't equal to negative KX. So we don't write F, so we write F double equal sign, really meaning like the elastic force, the spring force happens to be negative KX. I think but it is a little confusing because that is a law. It is a law. Whenever you're dealing with the spring force or the elastic force, it always is negative KX. So if I were really being technical, I mean, so I'm a little, and that is a GDP. I mean, really, to answer Melina's question, if you were ever stuck on any of these problems, homework, exam, and you're looking for a step 3 GDP, F equals negative KX definitely does count as a general definition of principle because it is a law about elastic. Maybe what I should really do from now on, I mean, I'm not going to do it because I don't want to confuse people, but like if I put a little subscript S on the F, like to stand for spring, or a little subscript E to stand for elastic or something, then I think that then I really would make that a triple equal sign. Like you can rely, as long as you know that by F, I mean the elastic force, not any force in general, not the net force, but the elastic force is always defined to be negative KX. If I had a little subscript there or something, or the word spring, then that would be a triple equal sign. I mean, okay, long answer.
Thank you.
Oh, but no, thank you. Thank you. And really, everybody, again, you know what I fear at night? You don't want to know this, but I fear at night that sometimes when people ask questions, then I make such a big deal of their questions that then other people are like, yeah, I'm not doing that because like he's just going to talk about me for the next 25 minutes. Like, and if that's the issue, I need to work on that because I do love these questions. Okay. And but really, what's the takeaway? Takeaway is when in doubt, stuck on step 3 of a homework or an exam problem, try to find a triple equal sign or a law to do it. Okay, now back to this. Okay, here's another something that we will get into more and more in this class. I think I said it to some of you last semester, but I don't know how many of you, and some of you never. You could just write this down right now, and this totally comes up in the end of homework 2, math methods. Okay, I'm just jotting this down. I am watching the clock still. For right now, it's just a truth. I will go back and expand on this later. But like if it is a triple equal sign definition that if you ever have two vectors, A and B, so two arrows, like two quantities with magnitude and direction, if you take their dot product, the dot product between two vectors, as we are doing in every one of these path integrals, whether the integral is a path integral or a closed path integral, you notice I'm always very specifically taking two vectors and dotting them together. What that actually means rigorously is you take the magnitude of one vector times the magnitude of the other vector, multiply them together, and then multiply by the cosine of the angle between them. And again, I will explain this more to people that have never seen this. I will later, but this is the fast truth of it. If you have any two vectors, A and B, and they're separated by the acute angle theta, to dot them is to multiply their magnitudes and then multiply by the cosine of the angle between them. What that actually does in the end is it's called the scalar product of two vectors. It gives you an answer in the end of the day that and please write this down, especially if you don't know this, just write it. I will explain it better later, or you can ask me private. But when you take the dot product of two vectors, what you're doing is you're getting a scalar result. You're multiplying two vectors in a way that gives you a purely numerical answer without direction. And B, how it's doing that is it's really giving you an answer that expresses how parallel the two vectors are. The closer they are to having the same direction, the bigger the answer will be. So it's a way of measuring how aligned two vectors are. That's what we're doing right? And again, this goes back to like when you're calculating work, you want to, if something is pushing something at an angle, you only want to account for the component of the force that is aligned with the displacement. Any other, like, so if you push at an angle and you push something horizontally, it's only the horizontal portion of your push that affects the horizontal motion of the object. So that's what the dot product does for you. That's a short explanation, but mathematically, you remember cosine of 0 is 1. Cosine of 90 degrees is 0. So like the closer the two vectors are, the bigger a result we're getting here. And if they were totally perpendicular, we'd get 0 as an answer. So the dot product says take one vector magnitude, multiply by the other vector, multiply by the cosine of the angle between them. In the case, but I'm just being careful and rigorous here because we need to know this for the course. But like in the case of the spring force is necessarily parallel to the displacement. There's no trick here. There's no angle. The angle is 0. So the cosine is 1. Oops, sorry. So the cosine is 1, I mean. Cosine is 1. So I'm just being technical and I'm just doing the integral carefully for you now. Okay, we have 6 minutes. So I'm getting that the work done from x equals some arbitrary spot, x equals not, to x equals 0 of like, so in other words, what I just did, it seems like I did nothing, but I just showed that in this case, the vector symbols go away. We don't have to worry about that because they're parallel to each other. So there's no angle to worry about. So I have the integral of negative kx dx. Now, x is the variable. It's the independent variable of integration. So I can so k is a constant. So it comes out of the integral. Actually, I'll do it like this. Right? So this is what I have here so far. Right? Now, before I go any further, now again, here's where we're in integral land here. In my heart of hearts, I think two things. I think one, no one should feel 100% solid with integrals. It's okay if we don't. But number two, if you feel solid with any integrals, or since you have had practice with some, I am feeling like the integral that we have, like you might feel tentative about setting them up and when and what, fine. But now that it's sort of set up and we're at this stage, hopefully you recognize that this integral is not so bad. You've seen way worse in your calculus classes. I'm just going step by step. I have this negative sign. It's kind of annoying. One easy way to get rid of the negative sign, I think you know, and stop me next time if you know, like from your other classes, I could get rid of the negative sign by flipping the limits. Right? Because the limits are what are going to come in when I evaluate, and they involve subtract. Like once you evaluate, you subtract one thing from the other. So if you just want to subtract in the opposite direction, that's like multiplying by -1, right? So I can do this. Stop me if you don't, but I think you know, I can just do this. I can get rid of the negative sign by flipping the limits of integration, right? So now I have k times the definite integral, and it's definite, right? Because but again, back to Claudia's thing, I know this is a conservative force because its closed path integral would yield 0. Now that I know that, I'm saying that potential energy applies. I could get potential energy for the force of spring because I know that the spring is conservative. So I'm not doing the closed integral anymore. I'm literally doing the integral from a spot to equilibrium. To calculate potential energy. And the integral of x dx, well, since I only have 3 minutes, I'm going to say it, but let's talk about it next time if you want to. How do I do this integral? I do the power rule in reverse, right? Remind me of that because of the fundamental theorem of calculus, right? Like an integral, to do simple integrals, I can do derivatives backwards. The integral is the antiderivative fundamental theorem of calculus. So So instead of multiplying by the power and then lowering the power by 1, I raise the power by 1 and divide by the power. You know what I'm saying? In other words, I think this integral is kx squared over 2 evaluated from x equals 0 to x equal, right? So at the end of the, sorry, you probably want me to go back there. I will in a second. But so at the end of the day, the spring potential energy of a mass at spot x equals 0 is 1/2 k x naught squared. Like that's, I'll go back to this page. I'll flip again. I know it's 2 minutes now, but like, right? Like, in other words, finish this. In other words, k x naught over 2 minus 0, which equals 1. Right? What we just figured out is the work done by a spring to bring a mass from some spot x naught back to the spot of x0. The work done would be kx naught squared over 2, or in other words, 1/2 kx naught squared. So for all time, what we just figured out now is the potential energy stored by a spring at any spot x naught is 1/2 kx naught squared. That's right. Hence, to get back to question 5, hence for a spring, 1/2 mv squared plus 1/2 kx naught squared equals 1/2. Like this is what we did for questions 4 and 5, right? So, because I promised. So the one thing I didn't do is get up to question 6, 7, and 8. I apologize. We will do that next time. You're not behind. I promise you're not behind. And wherever you are in the homework, just if this helped at all with anything with homework 1B, resubmit homework 1B. That's fine. If you think you're good, go on to homework 2, whatever. Just always do the next right thing. And I will continue with this next week. We are not behind. If anything, I owe you more feedback, but you are great. Thank you for paying so much attention for so long on Zoom. I hope you have a great, and I will hang out. Like if you have any questions right now, I'm not going until the last one of you goes. Like this is office hours now if you want it. So I'm here. But other than that, you didn't get a break. Yes. So have a great day. Exactly. Have a great day. Okay. Bye.
Can I just ask a quick question about this?
No, totally. Wait, and let me also just stop the recording for your sake or anybody's just so they know. But totally. Hold on one second. Yes, have a good day.